So hello and welcome to another video from sickmaths.co.uk, where you can find lots of free maths videos, both for the GCSE and A level, organised very nicely for the syllabuses. Right, this one is about circle theorems, and circle theorems are just about working out angles within circles. You'll see that in a second. So let's talk about these 8 rules. All this other stuff is about these 8 rules. So this is the real stuff. Okay, and these are quick helpful keywords to remember the definitions of the rules, which they often ask for, okay, in the GCSE exam. So here's our first one. Angles in a segment in the same segment are equal. So here's a segment, there's a segment. So segments are separated by a chord, which is simply a straight line, right? So these two angles are in the same segment. There's a tiny segment there, this is a large segment there. So these two angles are in the same segment. Now when you say two angles are in the same segment, it means they're both on the edge of the circle, okay, or at the circumference. And when you draw the two angles must be subtended by the chord, which means they basically, when I draw the two angles like this, I start from one end of the chord, go up and back down to the other end of the chord. Okay, that makes that angle. This angle go up from this end of the chord, up to the edge, to the circumference, and back down to the other end of the chord. So that's all part of the definition of angles in the same segment are equal. So if I wanted to make another angle, say start from here, up to the circumference and back down, that angle there would be equal to this angle and this angle. Okay, they're all equal to each other. Right, so that's angles in the same segment are equal. Another one, angles subtended by the same arc, where one is at the circumference and one is at the circumference, one is at the center. The one at the center is double the one at the circumference. Okay, that's the rule. What does that mean? Well, just to explain again what it means to say subtended. Subtended just means sort of anchored down. So your angle here is subtended by this arc. Arc is a part of the circumference basically, okay, because both the lines here are on the end of the arc, the lines that make the angle. So this angle is made by these two lines and they end on the arc. Okay, so that's that rule explained, and this rule can be drawn in a couple of different ways. This rule is the same as this obviously, but it can be drawn like this and like that. Okay, in each case you can see there's an angle at the center and at the circumference, and the center, circumference, center, circumference, always coming off two points. So these 2 points subtend these two angles, these 2 points subtend these two angles, and these 2 points subtend these two angles. So there are a number of ways of drawing this theorem, this rule. Angles in a semicircle are always 90 degrees. So here's your semicircle. Basically, if you draw an angle coming or subtended by this diameter is another way of saying it. So you start from one end of the diameter, go up to the circumference and back down, it will always be 90 degrees. Go up there, suppose, and go down, that angle over there would be 90 degrees. The tangents have equal length if you measure the distance from where they meet the circle to where they meet each other. Okay, you can explain that in your own way. What is a tangent, by the way? It's simply a straight line which happens to just touch the side of a circle. When it's a straight line and the circle is a curved surface, so it is only going to touch it. Unless it goes through it, then it won't be a tangent. A tangent just kind of sits on top, okay, or just touches it. Okay, so a very important result of this idea that these two lengths are equal is that if you connect the points where the tangents meet the circle, okay, you basically get an isosceles triangle, and therefore these two angles must be equal to each other. Okay, that's the main point. This is the main way this rule is actually used. We don't really care too much that these two lengths are equal. Once we say that, the main fact that we end up using in a GCSE exam is that these two angles would be equal as well if you connect them with a line like that. Okay. The next rule here is really simple. A radius meets a tangent at 90 degrees. Okay, there you go. That's really simple. That's a tangent. Let's go to the next one. There's not much to say about that. This one's called the alternate segment theorem. That means this angle in one segment is equal to the angle in the alternate segment. And when you say an angle in a segment, it means the angle is automatically at the circumference. When I say alternate segment, that means like the other segment. Yeah, alternate means like the other. Okay, so another way of looking at it is if you've got an angle here is touching this chord here, the angle opposite the chord is what it's equal to. So these two are equal to each other. If I make another angle here, it's touching this chord, so the angle opposite this chord is here, so this angle equals this angle here. Of course, this is a tangent, by the way. Yeah. If you got a line from the center of the circle and it meets the chord at 90 degrees, that means basically it's bisecting the chord. Or I could say it the other way around. If you got a line from the center and it comes to a chord and bisects the chord, that means it must be at 90 degrees to that chord. Here's another one. If you got a circle with, so you got a four-sided shape, and each corner is touching the circumference, that means it must be a cyclic quadrilateral. And a special thing about cyclic quadrilaterals is that opposite angles in a cyclic quadrilateral add to 180 degrees. Okay. So what else is there to explain? Well, there's these tiny things here. They're not circle theorems, but this one's derived from a circle theorem, this one here. Okay, it's basically saying a radius and a tangent meet at 90 degrees. So if that's 90, this is another radius, so that's 90 as well. These are tangents, by the way. See, these are two 90s, so that makes 180. And a quadrilateral's interior angles add to 360, so that means if this is 180, the remaining angles must be 180. It's not this rule, by the way, because this is not a cyclic quadrilateral, since this is not inside the circle, not touching the circumference of the circle. This is very simple. Basically, if you've got two radiuses, or two radii, I should say is the proper way to say it, again, you connect them, you get an isosceles triangle, so therefore this angle must equal this angle. This thing here is just kind of explaining how a typical circle theorems question looks like. So you got your question here, and you're told that this is 130 degrees, and you want to work out angle DAB. So this is angle DAB. So if you haven't used this three-letter notation to show what an angle is, the angle at the center is where the angle is, and they're effectively trying to make you draw the angle with your finger or something. So DAB, the angle is here. Okay, so what is that angle? Well, I've written 50 degrees because I'm just telling you the answer is 50 degrees, but how do you work that out? Well, as this thing says, the clue is you use the cyclic quadrilateral theorem, yeah, which means these two opposite angles must be add to 180 degrees. So 130 plus something equals 180, so that angle must be 50 degrees, because 50 plus 130 makes 180. Let's go to the next thing over here, BDA. So that angle here, okay, what is that angle? Well, if we use this theorem here, we basically got an angle in a semicircle, therefore that's 90. We already know that's 50, so this is a triangle, so it must add up to 180. So basically 50 plus 90 is 140, so the remaining angle must be 40 degrees. Let's briefly talk about the proofs now. Okay, we're going to try to prove this one here. So you draw it out and you make a dotted line. It's not much of a dotted line here, is it? But basically you end up using this idea that since you got two radiuses there, so this angle must equal this angle must equal to this angle. So let's call these this A and that B and that B. So for this angle here, in this corner must be 180 minus 2a, and this angle here must be 180 minus 2b, Okay, and therefore this angle here must be 360 minus this angle and minus this angle. Now since you are A-star students, hopefully you know how to do that, and you realise that it simplifies to 2a plus 2b. Do be careful to write it like this: 360 minus brackets 180 minus 2a close brackets minus new bracket 180 minus 2b close bracket. That's your tip to help you make sure you don't get it wrong. Anyway, so that simplifies to 2a plus 2b, and since this is a plus b, that's twice that one, isn't it? Yeah. Okay, so that's proved, and now that's proved, I can actually easily prove these two. Okay, for example, we're proving this one here. Now, the angle at the center must be twice the angle here, so I just make dotted lines here, and I'd say this angle is twice that angle, and this angle is half this angle. So if this is x, this is 2x, and if this is 2x, that is x. So you in effect have connected these two, and they're both equal to each other. So that one's proved. And this one is again using this idea because this is at the angle of the center, this is the angle at the circumference, and since this is 180, because we're using a semicircle, so this is 180, so half of 180 is 90, and we proved it. And finally, there's two more actually. You got the alternate segment theorem. Again, it's using this idea, and it's using this idea as well, because if this is n, then we would call this x, right? Because you got a dotted line here, which is your radius, okay? And angle between a radius and a tangent on 90 degrees. So this plus this x make 90 degrees. And if this is x, okay, and this is I've kind of cut it off and basically cut this isosceles triangle into two pieces, which makes it into two right angle triangles. Yeah, if this is x, and this is another angle here, tiny angle here, can you see it? Not the 91 here, but kind of drawn here. Basically it's the same as this angle on the other side, okay? That must be n, because if this is x plus n also makes 90 degrees, yeah? So basically, you A-star students, hopefully you can understand that, right? So if this is n, and we know this is n because these two right angle triangles here are the same, okay, so this is n, together they make 2n, and so we already know that angle at the center must be twice the angle at the circumference, so if this is 2n, that must be 1n, and we've again proved the alternate segment theorem using this idea here. Finally, using the alternate segment theorem, we're going to prove this theorem here, that opposite angles must add up to 180 in a cyclic quadrilateral. So this is a straight line, your tangent, okay, and you got an A and a B, and they obviously add to 180 because angles on a straight line add to 180. Okay, and this angle is equal to this angle according to the alternate segment theorem, and this angle is equal to this angle according to alternate segment theorem, but we already know that A and B must be 180, so A and B add to 180, and the theorem is proved.